Okay? So that's going to be a big issue. When it comes to Chapter 8 and 9, the sections that we talked about being on the exam, we're looking at two primary conversion factors. Okay? We're looking at AMUs to grams, okay, which is one way to look at it, which we said was the old way, but there was another way that we could convert that effectively gave us the same number, and that was looking at Avogadro's number. Okay? Does this sequence look familiar to anybody? It was on the study guide. Okay? So what's happening? Let's take a look at the left. What are we starting with?
Atoms and molecules.
Atoms and molecules. It then has an arrow going to AMUs. What does that mean? So good call. AMU means atomic mass. Didn't think of that answer. What we're doing is converting the unit. We're changing the unit from atoms or molecules into an atomic mass unit. Okay? To go through and do that, we have to have some way to relate those two units. How do we relate those two units? We look at the periodic table, and what does the periodic table give us? It gives us the relationship between our atomic mass and our atoms. Okay? So a single atom of iron is 55.85 AMUs. So what we've done is said for iron that 55.85 atomic mass units equals one, sorry I ran out of space, atom. We've just generated a conversion factor. If I want to convert something into AMUs, what do I need to do? Well, I'm going to have to put my 55.85 AMUs on top and my atoms on the bottom. Why? Well, if I want my end answer to be AMUs, where does that answer show up? Numerator, denominator. Numerator, which means 55.85 AMUs, it better show up in the numerator in all my work. Okay? What if I wanted to go the other direction? I wanted the number of atoms. Swap it. Okay? Instead of having 55.85 AMUs on top, we have the atoms on top. So what's happening in that backwards and forwards arrow? We're converting back and forth between AMUs and atoms. Where do we get that information from? We get that information from our periodic table. Okay, we get the conversion factor from the periodic table. If I now want to get AMUs into grams, okay, I need a new conversion factor. That conversion factor is there. That's a number that was given to you on the exam, along with Avogadro's number. If you want to convert between atoms and grams, do we have a direct conversion there? Is there an arrow that connects atoms to grams? Okay, said another way, do I see an arrow that does this? No. What does that mean? You have to go through AMUs first. You have to have some type of conversion factor to get you there. Much the same thing when we looked at micrograms to milligrams. Okay? We don't have a direct conversion between those two, so what do we have to do? We go through an intermediary. What's that intermediary? Grams. Same thing's happening here. Okay? With the micrograms and milligrams, and I see you. Okay? The issue with that is that we've seen those types of conversions before. In math, they tell you, what was that, the King Henry rule thing, shifting decimal places. That's fantastic when we go by powers of 10. Are we going by powers of 10? No. So what we have to do is come up with a formalized notation to allow us to do these conversion factors. Okay? So you have to have these conversion factors immediately available and accessible to be able to answer any of these questions. Okay? And it's not particularly easy because you keep thinking, well, I don't have that. Okay? There's a variety of places you can find that information. It can be directly given to you as a unit conversion on the front of the exam, which is why I said tear off the front page, so that you could now look at those unit conversions. Another place that you could find that conversion information, the periodic table, which is why what was on the last page. Periodic table, so you could rip it off and also look at that immediately while taking the exam. Okay? So that information was there. If we now shift to grams and we want to get into moles, okay, we'd need yet a new conversion factor to be able to do that relationship. Okay? We can also find that on the periodic table, okay, which was derived ultimately from Avogadro's rule, or Avogadro's number. And we could say that the number on our periodic table isn't just the relationship of some arbitrary mass unit and atoms. It's also grams to moles. We've now incorporated yet another unit that we can now convert between. How do we decide to use that conversion factor? Well, it depends on what we're trying to solve for. Okay? So one of the issues that people usually like to ask is, well, we didn't see example problems. Okay? Well, let's take a look at this. That first arrow gives you 2 problems. Next arrow gives you another 2, which means to work all those problems, I need to give you 4 examples for 2 arrows. Okay? Now I got another 2 in the next set, which gets me up to 6 different types of problems. And another 2 for the next set. Got 8 types of problems. We'd have to go through and do tons of different multiples, okay, so that you have a formula that you can build. It's not a formula. It's dimensional analysis. Follow the units. Let the units do the work for you. Okay? A lot of that unit work has to come from realizing you have these conversion factors and being able to use and find them. Okay? And that is exceptionally challenging. Okay? Once you get that pattern and start getting used to finding where those units are, it becomes like second nature and you process through it. Okay? Another common complaint with chemistry. Never have to do this outside of the classroom ever again. Dimensional analysis is used every single day. Okay? For every single field. Okay? It is something that we constantly do within our own heads as well. Okay? You can look at artwork from caveman period and go, oh, that looks crappy. Or you could look at your kids, but we usually don't say that looks crappy. Okay? But then if we go and look at something like Michelangelo and we see this perception of space and depth, okay? What did Michelangelo do and what did our brains do? Dimensional analysis. They organized how those shapes relate to each other and the distances that they're supposed to represent. Okay? And they were able to do that pretty quickly because the brain is an immensely powerful tool. The issue with the brain is that when we now put it into something that we haven't seen before, what do you try and do? You try and apply those same concepts that had no formal backbone behind them, and it fails. Okay? So when we go through and set up these problems, the reason why I keep asking these questions, what do we want at the end? What do we start with? What conversion factor can we put into it? Okay? The idea is to ask yourself those questions every single time and realize, at least at this point, okay, because it does get worse, we really have at most 4 conversion factors. Okay? And you have to be aware of where to find those conversion factors. Okay? And why do I say find? Because at this point, you don't have to have them memorized. Okay? So, when dealing with your conversion factors, you've got multiple places to check. Take a look at your text, take a look at the exam, and maybe your brain is that awesome, you can take a look at your brain too, because you memorized it. Okay? I can tell you right now that the only reason I've got any of these memorized is because I've had to do so many freaking problems. Okay? So, let's go through and work a problem. Okay? So we're going to start off with Harry has 100 pennies, Douglas has $3 bills, Sally has 30 dimes. What? Yeah, I know. Isn't this going to be fun? Harry wants to exchange his pennies for dollar bills. Douglas is infatuated with silver things, and so will only exchange his dollar bills for silver objects. What does Harry have to do to get his pennies converted into dollar bills? And how many dollar bills can he get? Ooh, good. We know the answer already. 1. What does he have to do? He has to give 100 pennies to Sally, get 10 dimes. Once he's got 10 dimes, what can he do? Give it to Douglas. Okay? Human brain, awesome. You guys did that conversion pretty quickly. Okay? Why do we have this type of problem? Okay? Because this shows up in mathematics all the time, and people go, this is dumb. We'll never have this issue. Because if Douglas doesn't want to trade, I'll go find somebody else and trade. You're absolutely right. Okay? But what happens when you don't recognize the things that you're trading? Okay? If you don't recognize what you're trading, now it becomes substantially more difficult because your brain doesn't have the pathway of something that you've done a billion times over. Okay? You might still even be able to do this conversion pretty quickly. Okay, why? We're running based on factors of 10. Okay? We can do pretty well with factors of 10, right? 2 times 10. I was going to do 2 again. 3 times 10. Okay? 10 times 10. Okay? 12 times 13. You're cheating.
No.
Okay. So, well, but again, and I know you weren't cheating, just so you know. That was really good. So, the only way that we really build these things up is we've beaten it into our heads and memorized these answers. Okay? So, if you want to get through chemistry, you have 2 options. You can memorize all the multiples of 6.02 times 10 to the 23rd and all the multiples of every element on the periodic table. Perfectly valid. I can accept that. Okay? That's a lot of memorization, and it's not going to help you. So what we need to do is come up with a way that we can formalize that conversion and that math into something that we can interpret. Okay? So when we go through and set this up, what we want to do is come up with what we want as our answer. I think I'm going to regret leaving it on this one. So what do we want as our answer? Okay? Harry needs to get... Harry needs to get his pennies converted into dollar bills. Okay? So what's our answer need to be? It needs to be dollar bills. Sorry, I just I couldn't do the other one. What is he starting with? He's starting, good call on the number, but I would actually argue that you shouldn't bring in the number yet. Really what I want to see are the units, so I'm even going to erase the number. We're starting with pennies. Okay, so now what we need to, did I spell that right? What we need to do is somehow get the pennies converted into dollar bills. Pennies is in the numerator, dollar bills is in our numerator. Okay? Does pennies show up in our answer? No. What do we have to do? We have to multiply by some conversion factor to get rid of that unit. Okay? What unit do we want in the numerator? Dollar bills. So we could try and go through and put in dollar bills. Do we have a conversion factor that works in this case? In this case, we don't have that conversion factor. What's the name? Harry cannot convert pennies into dollar bills. Because the only person that has dollar bills is Douglas, and he doesn't want those crappy looking pennies. Okay, so we do not have that conversion factor. Okay, this is where your brain is going to mess with you all the way through it. Okay, and this is why when we set these problems up and why they do it in mathematics is to force you to formalize your notation. Okay, what can Harry convert his pennies into? Dimes. Okay, you'll notice, what numbers did I put in front of the pennies and dimes? Nothing. Why nothing? Because the number is irrelevant. We need to set up our units. We can multiply and divide any multiple of these numbers any way we want, and it's still not going to get us our right answer if we don't have the proper units to match it. So we fixed our penny issue. Do we have our answer? No. What do we need to do? We have to get rid of the dimes. So dimes must show up in the denominator. Why? So it can cancel. What do we want to convert to? Dollar bills. Do we have that ability to convert in this case? Yes. He can trade with Sally. Sally? Yeah. What happens with our units now? Track our units. Dimes cancels, and we're left with dollar bills. Great. We now have the proper unit that we wanted for our answer. So now what do? Put in the numbers. What's the number in front of pennies? How do we know it's 100? Because Harry wanted to change all of his pennies across, which means we're going to take the exact total number of pennies that Harry has, and we've got 100. What's the conversion factor between dimes and pennies? 10 pennies is 1 dime. How did you know that? That's a conversion factor that you pulled from your brain. Okay? You have to make sure that you put the numbers in properly. What if you put 10 on top? You get the wrong answer. Okay? That's not the proper conversion. So you have to make sure that you use your conversion factors appropriately. What happens when we move to the next one? How many dimes in a dollar bill? There's $1 bill and 10 dimes. What happens? 100 divided by 10 divided by 10 gives us our $1 bill. That's the answer that we had shouted out at the beginning. Okay, so again, we're looking at these types of problems to try and set up a formalism, give you something that you can then apply to all other problems. Without this kind of notation, the unit conversion notation, you cannot solve problems that you've never seen before. How many of you have taken chemistry? Okay? If you haven't taken chemistry before, it becomes very, very difficult to process these problems because you aren't aware of those conversion factors. Okay? You haven't been doing it for however old you are now. Yes?
So on that last slide where you had the atoms or molecules A and then the arrows to AMU into grams, what about like if I'm doing atoms or molecules, does that just replace grams in that line?
Yeah, it's grams over moles.
So, you're asking about where?
Like,
Should I start? I'll start here. Tell me to stop.
stop.
Okay, so you're going grams to moles?
No, I'm saying like if it's asking for atoms,
Okay.
but I'm starting with grams.
Where's our conversion between atoms and grams? Do we have one?
The
What
mol
arrow
mass.
connects grams to atoms?
That's the atom. Oh, that's the atomic.
We have to go through the AMUs.
But that is okay.
That's going to be what allows us to convert our grams into
When I
atoms.
see AMU, in my mind it's separated from atom.
I know.
But it's the same thing.
It is the mass of one atom.
Okay.
So atomic, one atom, mass unit. What's the unit on a mass unit? It's a mass unit. We invented it. Okay? So when we look at one AMU, that is the mass of one atom.
So when you get the grams and you're going in moles, I get lost there too. I have no idea what's happening.
We'll look at a couple of specific examples that go through and do that. Okay? So the next fun question with this, what has the unit in the problem? I don't even know what that question was meaning to ask now. Okay? Could we put this into a reaction equation? What was our reactant? Pennies. Or Snorlaxy, fine, because that one's up there. It's actually Snorlaxi, not Snorlaxy, just so you know. What's our product? We're trying to get into Skittle farts. Kind of. Okay. Is there something that we needed to use to be able to get between Snorlaxy and Skittle farts? Dimes. Why would we write dimes above the arrow? It's effectively the catalyst that allows us to convert between these two. Okay. How many pennies or how many Snorlaxy did we convert? How many Snorlaxy did we start with? How many Skittle farts did we end with? 1. Cool, we have a balanced equation now that relates these two things. So here's the next issue. Okay, our unit is a count. It's 100 Snorlaxes. So that's what that, I don't know why I used has. Okay. Our unit is a count, a number of Snorlaxes, a number of Skittle farts. Why is this important? What if we change the unit to mass? Can we do that conversion? Okay. For instance, if we changed it now back to something that we can apply, let's make that Snorlaxy pennies. And let's make our Skittle fart dollars. Is a dollar bill exactly 1/100th of the weight of a penny? No. Okay. We could convert it into nickels, okay, or dimes. The mass changes. When we're looking at the equation, does it give us any information about mass? Absolutely not. It only goes based on a count, a number of things, okay, which is a really important thing to distinguish. Okay? So now that when we go through and try and deal with our reactions, if I want a mass, I have to get it into a count, a number of those things first. Okay? Once I have the number, I can then convert it into mass using the periodic table that relates the number, say it's a 1 atom, to a mass unit, or it relates the molecule or a mole of molecules into the mass for that amount. Okay? So when you're dealing with these conversions, you have to make sure that you move very carefully and slowly through each of the individual steps. Okay? So, how many oxygen atoms are in 0.24 moles of O2? What do we want as our answer? I'm going to say atoms is wrong. Try again. And take that a step further. Atoms of O2. Saying oxygen, it's implied, it's diatomic. I just want to make sure we're aware of that. Okay? So what did we start with? Okay? Throw in our conversion factor. We want to get moles of O2 into, can we really call it atoms? Okay, this is where it gets a little bit weird, and this is kind of obnoxious with this. An atom is how many different elements? It is 1. How many elements make up an atom? 1. Okay. Do we have 1 atom? No, we have 2. So officially this isn't atoms of O2, this is, okay, we can run with formula units or molecules of O2. Okay, we can't do atoms in this case, okay, or at least how we've got it written. So if we go through and attempt to solve this, we would now say moles into molecules of O2. What's that number relationship? 6.022 times 10 to the 23rd molecules of O2 per 1 mole of O2. You need all of those stupid units. Okay? So cool, we run that crunch and we get a number. Is that our answer? No, what's wrong? What's the question asked for? Oxygen, well, sorry, that was supposed to be a brackety thing. Oxygen atoms. What's our formula for oxygen atoms? Just O. What did we just solve for? O2. So we now have to incorporate a new conversion factor if we're going to get our answer correct. So our final answer, we wrote down initially wrong. It needs to be atoms of oxygen. Right now, we're at molecules of O2. Molecules. And what do we want? Atoms of oxygen. What's that relationship? There are 2 atoms per 1 mole. Heard a lot of people saying multiply, divide by 2. I heard both answers. Which are you supposed to do? Multiply by 2. How do you know that? Because the units solve the problem for you. As soon as you start punching into the calculator, oh, I just need to do this, you just need to get the question wrong. Okay? Write the problem out. Okay? That's why we have units. That's why we use dimensional analysis. Okay? Yes? Forgot what? I need more than that. Oh, okay. Okay. Should we try the next one? Moles of aluminum in that many atoms? Okay, I heard a big yes. So let's try it out. Sorry. Be picky about it. What do we want as our answer?
Moles of aluminum.
Good, following it up. Moles of aluminum. What do we start with? 3.42 times 10 to the 21st atoms of aluminum. Go through and deal with your conversion factor. What unit do we need to get rid of? What unit do we want? Moles of aluminum. Do we have a conversion factor that relates atoms to moles?
Yes.
Yes. What is that conversion factor? Avogadro's number or something, yes. Okay. And it is 6.022 times 10 to the 23rd atoms per 1 mole. What do? We have to divide. Okay? This, I think, did show up on the exam. When you go through and divide, you need to make sure you enter that into the calculator right. Some people are still having issues with that. Okay? And by still, this is really the first time that you really had to deal with it. Okay? You need to figure that out and make sure that you're getting that fixed. Okay? What size should this number be? Really big or really small? Okay, it should be relatively small because we're dividing by a very massive number. What are we starting with? A big number. So we're starting with a big number and we divide by a big number. What should our value be? Big divided by big. A billion divided by a billion. 1. Okay, approximate. What we're looking at is probably something on the order of 1. Okay, is it exactly 1? That approximation skill is now going to be a little bit more difficult. 10 to the 21st and 10 to the 23rd, okay, it will be smaller than 1. That's dealing with powers of 10. Okay, so a rough approximation should eliminate some answers. If you end up with a number that is really, really, really big, that doesn't make sense. If you end up with a number that is really, 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 really small, also does not make sense. Okay? So, another big one that we went through and looked at was a molar mass of a substance. It relates the grams to moles. Same place it's found on the periodic table, except instead of relating arbitrary mass units to an atom, we're now looking at grams, something that we can actually measure on our balances, okay, to moles, so a much larger number of atoms. Okay? So what we can do is decide what units we want to pull off of our periodic table. Either way, it relates the mass to a number of things. Okay? So, if we were going to convert the mass in grams, or get the mass in grams of 0.532 moles of copper, how do we start? Start at the end. What's our answer need to be? Grams of our copper to nitrite. Tricky thing. What's the issue with answering this question? You need to know what? You need to know the formula for copper nitrite. Without that formula, you cannot solve this problem, which means you need to know Chapter 6, nomenclature. What we're looking at is copper, what did I say, nitrite? CuNO2. I am still working on trying to figure out how many of the polyatomic ions you need to have memorized if you've got to have them memorized. Okay, it's still in the work for the final, yeah. Okay. Before we even move on, is our formula correct? How do we check that? Charge on copper is How do you know it's plus 2? Roman numeral means the charge. Charge on nitrite. -1. How do you know that? You had it memorized or look it up. Okay, you've got the textbook. You can't look it up on the exam, which is why you'll either have to have stuff memorized or I'll give you that information. Is it balanced? No, we need 2 of those. Okay, what do we start with? We start with 0.532 moles. I'm just going to say CN because I'm lazy. Okay. What do we want to do? Moles of CN needs to cancel, and we need grams of CN in our numerator. Do we have a way to convert between grams and moles? This slide is interesting. What does it say at the top? We have a way to convert between grams and moles. Okay? To do that conversion, we have to know the mass in 1 mole of copper nitrite. Do we have a way of figuring out the mass in a mole? Yeah, we look at the periodic table and we use the molecular mass for each of the elements and we add it up. So the number that we would have to put in front of grams would be the mass of copper. Keep looking in the wrong spot. Mass of copper. Oh yeah, I find it. 63.55 plus 14.01. What was that last part? Why do you multiply by 2? There's 2 of them. Plus?
16 times 4.
Why do you multiply by 4? There's 4 of them. This gives us our grams per mole for that molecule. I don't know what that number is, but it's going to be some number. 63, 30, 60. What was that? 82.8? No.
Oh, I mean,
150 grams per mole. We can put in, whoops, our 150 per 1 mole. We now punch it into our calculator and we get our final answer. Okay? So the idea is that you have to process each of those individual steps. It takes time, it takes effort, okay? But eventually you'll internalize it. And instead of writing out 63.55 and all that junk, you'll punch that immediately into the calculator, get your number, and write that down immediately into it. Okay? At this point, you should be writing out each and every single one of those steps. Worst case, this goes for the show your work stuff. Okay? To do this problem, did you need to know what the answer was? Or the units on the answer? We need to know that to solve it. Were you given that information? What could you have written down? Equals grams of copper nitrite. What did you just do? You told me that you could interpret the question. Okay? Part of an exam is to do what? Test your understanding of the material. What did you just do? You proved to me that you could interpret at least what your answer's units needed to be. Okay? Is that a lot of work? No. Is that something that I can give you points for? Yes. Leaving anything blank is a bad idea. The only time that that makes sense is when you are penalized for guessing. Okay? There's only very limited tests that actually do that to you. Okay? And I think it's only the SAT. Okay? So, yes, please, guess. Put something down. Do not leave it blank. Mass in grams of 2.55 times 10 to the 23rd atoms of lead. Oh, and she left. This is what she had questions about. Bummer for her. What do we want as our answer? We want grams of lead. It's a simple interpretation, but we could write out lead or we could write PB. Why would we write PB? You're lazy. It's shorter. Okay, I like that. Stick with that. I'm lazy too. Okay. We're going to need that information anyway because we need to know something about the lead atom, and in particular, its relationship to its mass. So what do we start with? Okay, I'm going to kill numbers on it for the moment. Atoms of lead. So we take a look at our conversion. We want to get rid of our atoms, and we want to get 2 grams. Do we have a way to relate grams and atoms? No. What's that? 1 AMU equals 1 gram. Do we have AMUs? No, we have atoms. Okay, so yeah, you got to be careful and be very specific on what your units are showing. We don't have that relationship. Okay, can I convert the atoms into something else? I could go into moles of lead. Okay, does that get me closer? Well, I want to get rid of moles of lead, and I want grams of lead. Do I have a conversion factor that allows me to do that? Where is that conversion factor found? Our periodic table. Where's our last conversion found? This guy? That's Avogadro number. I just brain farted and couldn't remember how to spell it. Okay, so we've got Avogadro's number. What is Avogadro's number? Times 10 to the 23rd atoms. Why do I keep waiting for that atom statement? That's where it's located in the conversion factor. If you don't include that unit with that number, you could multiply and get the answer wrong. What's our conversion factor between grams of lead and moles of lead? 1 mole equals, I think you said 207.2? 207.2 grams. We can now also put in our freaking huge number, 2.55 times 10 to the 23rd atoms of lead. Punch it into our calculator and we'd get our answer. Okay? Follow the units. Treat the units like a game. You need to get from point A to point B and make sure the unit shows up in the proper spot, either top or bottom. Do whatever you got to do to get it into that spot. Okay? And you must use the same conversion factors. You can't invent a new one. Okay? How easy is this? With a little bit of practice, it becomes intuitive and quick. But to start with, it takes time. I apologize for that, because what I did was tested you on this material before you really had time to practice it. Okay? Which means you now have had since Tuesday to practice this material. Okay? So initially I was going to test you on it again today, but I thought that was a bit mean. I was just going to put you in the same boat, no time to practice it. So we'll test you again on it on Tuesday. Okay? As far as that test time, you get 15 minutes. Okay? And it's going to be roughly 10 questions, maybe a few less or a few more. Okay? So you need to go through and practice this like crazy until it becomes intuitive and very natural and quick to get through so that you can solve this. Where do you have practice problems to now work on this type of material? Textbook is a good option. There's another one that I would argue is going to be, hint, hint, even way more important. I posted the exams. Okay? Look at the exams and evaluate those questions. Make sure you understand how to do all of those questions when you're looking at your conversions on the exam. Because those might, hint, hint, show up again. Yeah.
Is it going to be like point for point, or is it going to be like half?
I haven't quite exactly decided how to do it. I might very well do it point for point. Okay? So, we could continue to go through and do these. Okay? You should have some reasonable practice with those. The next one I really want to get into is going to be looking at Chapter 9. Okay? Ultimately, all Chapter 9 tells you, Okay, or it does a couple big things, actually. The first thing, which we've already started to address, is that we have to look at a complete unit. Grams is now useless. I need to know what that's grams of. If I don't know what it's of, I can't use it in Chapter 9. Same thing with moles. We have to specify what we're working with and what we're looking at. Okay, why? Because now instead of just converting one thing into another, okay, of that same type of species, just converting either mass to atoms or to moles, I'm now converting that atom into a different atom or a different molecule. How can I do that? That seems pretty impossible. We've never learned how to convert one group of molecules into another group of molecules. That just doesn't make any sense. What type of reaction does this look like? I know I haven't given you a whole lot of... We're looking at a decomposition. What happens in a decomposition reaction? Separates into two things. What did we just do? We took a group of atoms, 2 hydrogens, a carbon, and 3 oxygens. How did I know those numbers? Came from the formula. Don't give me that from the formula kind of thing. You need to be super aware of this. I'm seeing some mistakes happen here. I'm actually slightly concerned because it might be a mild form of dyslexia. Okay? That's extremely serious when you're dealing with these things. So please, if you get your exam back and you look at some of your work and you think that's happening, okay, please talk to student services and see what's going on. How do we know there's 2 hydrogens? The 2 after it applies to the atom immediately in front of it. Okay? How do I know there's only 1 carbon? There is no number immediately after it. This 3 after the oxygen applies to the oxygen and the oxygen alone. It only applies to what's directly in front of it. Okay? So one case is that where there's some misconception on what those numbers mean. Okay? Hopefully we've got that clear now and you understand what's going on. Where it could be an issue, what does the 2 mean now? It goes to the parentheses. There's 2 of that parentheses set, which means how many carbons are there? 2. Okay, now the 2 applies through because we're looking at the parentheses being multiplied by 2. Okay? So make sure you understand what those numbers mean and where they apply. Okay, so if we go back to the equation, we took one grouping of atoms, 2 hydrogens, a carbon, and 3 oxygens. And what did we do? We ended up with 2 groupings of atoms. One with 2 hydrogens and 1 oxygen, and one with 1 carbon and 2 oxygens. Did we just change the grouping of atoms? Yeah. Okay. What we've now done is converted one molecule into other molecules. That conversion is given to us in the equation. Okay? If we look at this equation, if I start with 1 molecule of H2CO3, how many molecules of water can I produce? 1. How do I know that? We use the equation as a summary of parts. Okay? H2CO3 will decompose into 2 parts, H2O and CO2. What we've now generated from that is a conversion factor. 1 molecule of H2CO3 equals 1 molecule of H2O. Huge. We now have the ability to convert molecules, not just from one element or one molecule, but into a different type. Okay? The only way we can do that is through the equation. We need that reaction equation. What makes this even more important is how do we get the numbers in front of this conversion? Where did you get the 1 from? The coefficient in your balanced equation. What if your equation's not balanced? You don't have a conversion factor. You must balance the equation first. This was arguably the hardest question on the test, and you got lots of partial points for it because I made a couple mistakes with that. Okay? To set it up, the very first thing you needed to do, balance the equation. Okay? You know how to balance. Okay? That was very clearly proven to me based on your scores within the balancing section. Okay? Nearly everybody did very, very well within the balancing section. Okay? You do know how to balance. So if you're given something that's not balanced, balance it. Okay? Worst case, hopefully your balancing skills are quick enough that you, at worst case, waste 2 seconds to go through and spend the time to balance it. Okay? Those 2 seconds can be worth it, particularly if they turn into partial credit. Okay? So, textbook goes through all sorts of fun things with this. They gave us a new equation here. You'll notice that our conversion factor is not 1-to-1 all the way through. Okay? If I start with 1 mole of nitrogen, how many moles of oxygen do I need to react? 1. How do I know it's 1? What's the coefficient in front of the O2? 1. Okay? If I give you an unlimited amount of oxygen and 1 mole of nitrogen, how many moles of nitrogen oxide can you produce? Technically nitrogen monoxide. It's a trickier question. We said we started with 1 mole of NO, and what are we trying to get to? Moles of NO, right? So I heard a lot of 1s out there. Whoops, that's not, we started with 2, right? N2. I want to convert moles of N2 into moles of NO. What's the relationship between those? What number should show up in front of the moles of NO? How do you know it's 2? The coefficient in front of the NO is 2. That's a 2. And our answer becomes 2. Okay? That's why we have the balanced equation. That's why we use conversion factors. Okay? The gut response is just to start to throw out numbers. Don't throw out numbers. Put down some numbers, put down those conversion factors that allow you to do that conversion. It takes a little bit more time, but it also gets you the right answer. Yes?
I realize these are diatomic, but just for humor's sake, let's say that the O2 was a single, no subscript. But I gave you 2 oxygens, if I said 2O. You do the same thing.
Okay, so for humor's sake, let's look at a new equation so that way we don't have to deal with this guessing. You're saying 2 oxygens. Yep.
You were trying to do conversions there.
And we want to get to...
Could you necessarily use the coefficients?
Okay, so new equation. If I give you 1 mole of N2 and an unlimited amount of oxygen, how many moles of NO can you make? 2. So what we did is the exact same question we just asked. Even though the equation changed, our answer was the same. Why? Because the coefficients in front of those numbers didn't change. So now let's get more on where I think you were asking is with our oxygen. What if I give you 1 mole of oxygen? And I now want you to tell me how many moles of NO you produced. Okay, same thing. I want to get rid of moles of oxygen, and I want moles of NO. What number shows up in front of the NO? 2. What number shows up in front of the moles of O? 2. What do we get? 1. Okay. Let the conversion factor do the work for you. Okay. So your balanced equation gives you a lot of information. Okay. It's now just applying that information, putting it into a conversion factor. Okay. Does that answer your question?
I get that. I'm getting hung up on the coefficient like the N2 to 2O. Don't think of that, man.
Okay.
I'm looking at it like how to break coefficient rules off.
You don't have to. There's no coefficient rule breaking. It holds true. Okay? So with this one equation, we have an impressive amount of conversion factors. We have 6. So for all of those, I didn't see a practice problem. One practice problem for this, I'd have to give you 6 different examples. Okay? That's a lot of practice problems. Okay? It all is going to depend on what you're trying to get to, which is why I'm giving you the fundamentals on what you have to set up to go through and do the problem. Generate that conversion factor, then use the conversion factor. And you need to use it by setting up your game. Get across to your appropriate units. Do whatever you've got to do to get those units to cancel out. Okay? Absolutely challenging, but I'm positive you guys can do it. Okay? Super, super confident that you can. No, it's not. This is textbook. Freaking textbook. Should be 2 moles of NO. Yeah, you're right. One of the reasons why our future lectures are not going to be based on the textbook. Okay? So, take the information from the equation, set it up into the correct ratios. In theory, they got the rest of the ratios right. Follow the unit. How many O2s are there? The coefficient is 1.
Yeah, but you need...
Coefficient is 1.
That's what I was asking.
This is your conversion factor. You still have to be able to convert across.
Yeah,
So,
one oxygen.
let's back up.
You need 1 mole of O2 and then 2 oxygens. Perfect.
So, let's give you 1 mole of O2. How many moles of NO can you make? Your conversion factor. Moles of O2, moles of NO. What number shows up in front of the NO? Yeah, and that's accounted for in the balanced equation. That 2O2 is what gets you that number.
How do we know that who's supposed to go there?
What number shows up in front of the moles of NO in your balanced equation? 2. Okay? The balanced equation every single time will give you the proper conversion factor. Every single time. There is no exception. Okay? Use the balanced equation. Use the coefficients from the balanced equation. Why do the subscripts become important? To balance the equation. So our subscript shows up or becomes important because that's how we balance the equation. That's how we know we needed 2 in front of the NO. That's where that coefficient is, or that subscript is playing a role. It's allowing us to balance the equation properly. Okay? It's now been factored in both cases. Yeah.
So in the sense that 2 in front of the NO is the same thing as the 2 subscripts, kind of?
I really don't want to make that equation.
Or like just this
Kind of, sort of. It's there for similar reasons, yes. Because nitrogen and oxygen are diatomic, we need the 2. Okay? Because there's 2 of each, I have to have 2 NO. Okay? So they're definitely related. I don't want to say they're the same. Okay?
If I had O100, 1,000.
So, careful. Let's go through and change your question a little bit. If I give you 1,000 moles of oxygen gas, okay, 50, 52? Okay. So here's where I think your question may be. What if I give you 50 moles of oxygen element, the oxygen atom? Does that problem work? If I give you, maybe this is what you're getting at. I asked for 50 moles of oxygen atom.
I think you find the subscript to be 50.
You can't make the subscript 50 because then you change the formula. The formula of oxygen gas is O2, period. You can't change that subscript.
I'm just wondering because there's 2 atoms in every O2.
Well, I think that's what we're getting at here. Let's say we take oxygen atom, and I give you 50 moles of oxygen atoms. Can I do this problem? No. Why not? Look at the balanced equation. Where does oxygen atom show up in my equation? It does not. I do not have a conversion factor to relate moles of oxygen atoms into the moles of nitrogen oxide. In this case, no. Our balanced equation does not give us that information. We do not start with moles of oxygen atoms. We start with moles of oxygen gas. Two different species. Okay? So that conversion does not work because this is O2, this is O. You can't do that conversion. Okay? So when you go through and process your mole-mole relationships, ultimately what we're trying to deal with, oops, that might have been nice to have an equation. What we're trying to do is relate things across the equation. So if we start with 2.25 moles of nitrogen, how many moles of oxygen gas produce? So just like we've done every other problem, where do we start? Equals units. Moles of oxygen. Let's be careful. What's our formula going to be for the moles of oxygen? Why does it have to be O2? Oxygen is a diatomic element. It must be specified as O2. The only time that you will look at any of your diatomic elements written as an atom is when we specifically say it is an oxygen atom. Okay? That implies 1. That is the only time you can write that. So that is our answer. We want moles of oxygen. What do we start with? Okay, I'm going to argue the number is useless. Moles of nitrogen. What's our formula? N2. Again, attempt to convert. Moles, N2, needs to be in the denominator so that the units cancel. What needs to show up in the numerator? Moles of O2. What's the relationship between those two? 1 mole of O2 produces 1 mole, or needs 1 mole of N2. Do our units cancel? Yep. So what can we do? We can now put in our numbers. How many moles of O2 do I need to react? 2.25. Follow the conversions. Follow the units within your conversions. You must make sure that your units are correct.
Like the moles of the O2 and the N2, we got that from the product side or the reactant?
We got it from the balanced equation. And all honesty, I don't care if it's reactant, product, both reactants, both products, one reactant, one product. It doesn't matter. We're assuming that this problem to solve is based on this equation. Doesn't matter where they show up within the equation, as long as the equation is balanced, that's where my conversion factor comes from. Okay? Other questions? Okay. Last thing, and we'll look at numbers on this on Monday. Okay, and this is where it's going to become really, really painful. I'm not going to lie at all. Your limiting reactants and your percent yield calculations, which is a lot of what Monday is going to require a very firm understanding of everything else we've talked about. Our conversions from Chapter 8 and our conversions now with our balanced equation. Okay? To determine what's happening with a limiting reactant, what we need to do is look at our equation and then try and decide, based on the information given, how many things can be produced. Okay? And we typically, when we're looking at a limiting reactant, look at what's produced. Why? When you run a reaction, do we care necessarily about our reactants? Okay, when you go into lab, you just mix two things and go, oh yeah, that was cool, I just mixed them. Well, that might have been a bad question. When you go into lab, what are you supposed to do? You mix two things, you go, oh cool, something changed. That something changed is the product. Why do we make you mix those two things? So that we can get the product. Why do we mix cheese with bread? Because bread on its own is freaking boring. And cheese, well, cheese is pretty awesome. But we mix them so that we can get a sandwich. Okay, we're concerned about that final product, okay, our sandwich. So when we go through and evaluate our reactions, now what we want to go through and do is decide if I'm going to try and predict how many sandwiches I can make. I know I need 1 slice of cheese, which is a wheat sandwich, and 2 slices of bread to go through and make my sandwich. Okay? When I go into the store and buy my cheese and bread, apparently I'm lazy, okay, and I buy it as slices. Okay? How many sandwiches can I make out of that? Another common example that you could work with before we take off. You go into the store, do a barbecue over the weekend. Typically we'll cook up maybe some hot dogs. Hot dogs come in packs of 6. And the buns come in packs of 8. Freaking irritating and annoying. Okay? You can't get a perfect ratio there. Unless you're throwing way too much bread, and that's just not nice. Okay? So what we have to evaluate is look at that limiting reagent problem. So in the case with the hot dogs and the buns, if I want to match that up, I then have to buy 8 packs of hot dogs. Well, I could probably get away with a smaller amount. 3 packs of hot dogs and... I did all the math wrong. It's late. 4 packs of hot dogs and 3 bags of buns. Okay, to go through to get it. And then I have 24 pairs. Perfect, they're all matched up, but now I got to throw a bigger party. Okay? So that's what we're going to be dealing with when we're looking at our limiting reactants. We will run lots and lots of calculations on Monday.